We now talk about how to disprove universal statements. So disprove means the opposite of proof. That means we are not proving it's true. We are trying to prove that it is false. So in other words, we prove it is false. How do we prove a universal statement? Well, first of all, universal statement is equivalent to universal conditional statement, vice versa. We talked about this in the last unit, how to convert back and forth. Basically, if you can recall, if we combine these two, that becomes a universal statement. So again, when we say disprove universal statement, that's the same as disproving universal conditional statements. Okay, now let's talk about how to disprove that. So to show this is false, to show this statement is false, is equivalent to show its negation being true. Negation is true. Okay, so now how do you show that the negation is, well, let's first take a look at its negation. The negation of this universal conditional statement is there exists x such that p of x and not q of x. All right, so if you want to refresh your memory how to negate this guy, I would suggest you go back to last unit and take a look at how we actually negate that guy. But anyway, so now how do we show this is true? That means we are going to find x. We are going to find x, just one x, so that p of x is true, but q of x is false because there's a negation there, right? So q of x is false. That's how we show it. So we want to show p of x is true, but q of x is false. And this specific particular value, we call it a counterexample. So a counterexample is enough to show that a universal statement being false. This is one pretty famous example. This statement, this conjecture was proposed by Euler, who was born in 1707, a little more than 300 years ago. This statement says, for all ABCD in non-negative positive integers ABCD, a to the fourth plus b to the fourth plus c to the fourth can never be equal to d to the fourth. In other words, there's no way that the sum of the 3/4 powers of three integers will be equal to the fourth power of another integer. There's no way this can be true. That's proposed by Euler. Actually, it was disproved by this guy about 200 years later. Of course, another smaller counterexample was found later by, I think, by computer search. So this is one counterexample. In this example, you can check a to the fourth plus b to the fourth plus c to the fourth is actually equal to the d to the fourth. Okay, so now I want to relate back to here. Again, earlier we say a universal statement, like this is a universal statement because this is a for all statement, and then this is your q of x, right? Please note that universal statement can be written into universal conditional statements so that these two are combined and become two here, okay? So in other words, how do you show this is a false statement? You want to show these two are true. You want to find p of x is true, and then you want to find a value x so that p of x is true. Basically, you are finding some value so that this is true. But this is false. That's what's exactly happening. So it was found that for integers, they're all positive integers, but this is false. So therefore, this constitutes a counterexample. Now let's do some practice together. Let's look at the first example. For all non-negative real numbers a and b, square root of a plus b equals square root of a plus square root of b. So we want to prove that this is false. Disprove this statement. Again, I can look at it two ways. First way is you know, this is a universal statement. Even though this doesn't look like this form, it should essentially it is equivalent to this form. So what's the goal? We are trying to find a value x so that this is true, right? P of x is true. But when you combine these two together, that's exactly what this is. So basically, we are trying to find non-negative real numbers a and b, so that this is false, right? Then that counts as counterexample. Or you could certainly rewrite this into universal conditional statements. And how do you do that? You just break this into two pieces. So I see that two adjectives here. One is non-negative number, the other one is real number. So obviously, real number is larger set. So I'll begin with for all a, b real numbers. So because if a, b are non-negative, that means greater than or equal to 0, then square root of a plus b equals square root of a plus square root of b. So please note that these two combined is equivalent to this whole thing, right? So in other words, we want to find a and b so that this is true, but this is false. Or you just, sometimes in the future, you may, once you are proficient, once you are getting very good at reading, you sometimes really don't need to, but this is certainly a good practice. Okay. All right, so let's try to find, so here's a counterexample. So can you come up with a and b so that they're both non-negative, but square root of a plus b is not equal to square root of a plus square root of b. That's your goal, right? Okay, now actually I feel like I'm gonna call 3 and 3, okay? 3 and 3. And then take a look at is 3 and real numbers, square root of, yeah. So maybe I'll pick some nicer numbers. 4 and 4, that might be very, very clear. Then square root of a plus b will be square root of 4 plus 4, which is square root of 8, right? And square root of a plus square root of b, which is, I need a little more room here, which is equal to square root of 4 plus square root of 4, which is 2 plus 2, which is 4. Then you can see that then square root of a plus b is not equal to square root of a plus square root of b. This counts as an counterexample. Now let's take a look at the second one. Second one is nice now because it's the if-then statement. So therefore, we are trying to find m and n that are positive integers, and at the same time, m times n is a perfect square. So find m and n so that this is true. Now you also want to make sure m and n are not perfect square. So also, meanwhile, you have to make sure this is false to disprove this statement. So here's the counterexample. Say let m be 3, m be 3, then m times n is 9, which is a perfect square. Okay, so see, I pick m and n so that all these are true. Now let's see, but m and n are, because 3, right? 3 are not perfect square. So therefore, this is a counterexample that disproves this statement. And for last one, again, you can, even though this is not a universal conditional statement, it should be still the same thing, as long as we are trying to, because these two combined will be the for all. So we are going to try to find something this is true, but this is false. That we'll consider as a counterexample. So sometimes when it is clear, you really do not have to rewrite it into if-then statements. However, again, I don't want to say that this is not important. Sometimes it is a very, very good idea to rewrite a universal statement into if-then statement so that you know what's given, what is to be the conclusion that you want to prove. So, but for the case like here, which is very clear, we are trying to look for positive integer n, so that this is not a prime, right? We are trying to look for one specific example. So here's the counter example. So we are going to let n be, so think about it. I'm going to pause for a moment. So the f of this guy, so this is the guy we are trying to find. So n squared plus n plus 41. Okay. Now here's the hint. Take a look at 41, which is prime. How about we just let n be 41? So what is f of 41? It will be n squared, which is 41 squared, plus n, which is plus 41, and then plus the last 41, right? And this is actually equal to, if you factor out the 41, then you're left with 41 plus 1 plus 1, which is 41 times 43. So do you see that we successfully find a number so that this is true? See, 41 is a positive integer, but this is false. This is not a prime. It's not a prime. So therefore, we successfully disprove this statement. All right. Now, we've seen several techniques on proving, disproving. It's time for us to take a look at one important type. So this is a very common statement. Like we have a universal conditional statement. All universal statements, they are equivalent. How do we prove this statement? So this is a universal statement for all. There are two methods. One is called a method of exhaustion. So what does that mean? That means you have to test every single value x in the domain so that you know when this is true and this is true. So this is only appropriate if we can test every single value. That means you have finite number of elements in D. So even then, sometimes it may be impractical when the D is pretty large, right? So this actually is not that popular, but certainly we want to introduce this particular one. For instance, let's take a look at this one. For all n in Z plus, that means for all positive integer n, if n is less than or equal to 10, then f of n equals n squared plus n plus 41 is a prime. How do we show this is true? Then we are going to check all the n less than or equal to 10. That means n is 1, 2, all the way up to 10, right? So we just check that one by one. So let's check. Proof. F of 1 is 1 squared plus 1 plus 41, which is 43. Prime, right? So it's a prime. F of 2 equals 2 squared plus 2 plus 42, which is 46, which is 47. 6 plus 41, which is 47, which is prime. F of 3, which is 3 squared plus 3 plus 41, which is, this is 9, 12. 12 is 53, which is prime, right? And then you just continue. F4, which is 4 squared plus 4 plus 41, which is 61, which is a prime. And F of 5, 5 squared plus 5 plus 41. 5 squares 20, 30, 71, which is a prime, right? And f of 6, so really there's no trick, you just do that. This is actually turned out to be 83, which is a prime, and f of 7, and you turn out to be, I actually have that done, 97, and f of 8 is 113, which is also prime, f of 9, which is 9 squared plus 9 plus 41, 131, which is also prime, f of 10, which is 10 squared plus 10 plus 41, which is 151, is also prime. So we just check them all. Therefore, we can make a conclusion. Therefore, you can just copy it down for all n in Z plus, if n less than or equal to 10, then this f of n is a prime. Okay, I skip copying down this expression, but this is how we are gonna prove that. All right, so this is obviously even for 10 numbers, like the domain has only 10 numbers, it's a little tedious. So therefore, this method of exhaustion oftentimes is not practical. It's good when you have a small domain, and then we can check one by one. Otherwise, the next method, which is the most important method, is called the method of generalizing from the generic particular. So this is also, we just call it the method of direct proof. This is usually the most important method, one of the most important method, I would say. The other method is proof by contradiction, which is also, or proof by counter example in the future. Those are the other two very powerful methods. Those are the three methods that we should focus on. Now we are gonna take a look at this method in the next video.